Hi there. There was a request for me to talk through some of these multiple choice things, which is probably better than me trying to write them down or to explain them individually. So I'm going to make some videos where I rather quickly go through how I would do all of these problems. So again, it will be fairly quick. You may need to pause and rewatch things if they're a little complicated, but I'll do my best to make my thought process clear. So for problem number one, any limit problem, our first instinct is to plug in. If I just plug in, I have 4 minus 2 over 4 minus 0, which is 2 over 0. And that's never going to resolve to something. This is fundamentally weird. The graph has a vertical asymptote or something like that. So this would be D. Number one is D. Okay, for number two, we see x is going to infinity. So hopefully you remember that when we have limits going to infinity of something with a fraction, only the biggest terms in top and bottom matter. So up top, only the root x matters. In the bottom, only the negative 3 root x matters. These 4s don't really matter in the long run. And so that ratio is negative 1/3, which would be A. All right, let's look at 3. So one thing we'll point out here, right? They're kind of tricking you. E to the natural log of u is just u. So we have y equals u over u, which is 1, and the derivative of that is 0. Theoretically, you could do this by a really hard application of chain rule and quotient rule, but I think what they're testing here is your ability to notice that this is actually quite simple. All right, for number 4, we're using a tangent line approximation to estimate something. So let's just note here, this is really close to x equals 0. So let me switch to a different color, my work for number 4. And just so you know, on the real AP, usually it's a maximum of 2 problems per page. They give you a ton of space for your work. You don't have to cram it in margins the way I'm doing it here. So f of 0 would be the square root of 9 plus sine of 0, which is 0, which is 3. So the idea is this y value is presumably very close to 3, but we've changed it a little bit. So now let's think about the derivative. F prime of x would be 1/2 times 9 plus sine of 2x to the negative 1/2 power times, by the chain rule, the derivative of what's inside, which is 0 plus cosine 2x times 2. So f prime of 0 would be 1/2 times 9 to the negative 1/2, because sine of 0 is 0, times 0 plus cosine of 0, which is 1 times 2. So I'm noticing this is 2, this is 1/2, they cancel out. And I'm left with 9 to the negative 1/2, which is 1 over root 9, which is 1/3. So that's the slope. So the idea is the slope is 1/3. So if my change in x is 0.06, my change in y would be 0.01. So you can kind of think that we were at this point 0, 3, and we're following a line with a slope of 1/3. If I go over, if I go over by 0.06, I go up by 0.02. So my new y value should be around 3.02, which is D. All right, for number 5, they have a table here. The rate at which school children are dropped off to school on a certain day is modeled by this. So this is a rate. Let's just emphasize that. What is the approximate number of students dropped off at school in the first 30 minutes using a trapezoidal sum? So first of all, we want to realize that we're going from a rate back to an amount. So what we're trying to figure out for number 5 is the definite integral from 0 to 30 of this rate at which they arrive. That's going to give us the total number of students who arrived. And it says to use a trapezoidal sum. So for a trapezoidal sum, what you want to do here, and you don't have to draw the picture, but the visualization might help. We know values of this at 0 and 10 and 25 and 30. So let's think about a y-axis here. When we have time is 0, the value is 10. When time is 10, the value is 18. I guess I'll put that over here. When time is 25, the value is 20. And when time is 30, the value is 24. We want to find the definite integral, which is like an area, and it says to do a trapezoidal approximation. So the idea is we can draw 3 trapezoids. Area of a trapezoid is base times average height, if we have this kind of orientation. So here the base is 10, and the average of those heights, 10 and 18, you can read it off the table, you don't really need the picture. The average of those 2 heights is 14. Here, the base is 15 units wide. The average of these 2 heights is 19. Here, the base is 5 units wide, and the average of those 2 heights is 22. This is perhaps a little more arithmetic than they would ask you to do on the calculator free section. Not that it's that hard, but they don't want you to get bogged down in this. So what do we have here when we add these together? 140 plus 15 times 9. I'll do that in a second. 15 times 9 is, 15 times 19. I'll just do it. 95 is 285. So when I add all those together, 140 plus 285 plus 110, this is 3, looks like I get 535, which is choice B. Okay, number 6, we're just taking a derivative. I'll remind you that sine to the third means we're computing that sine value and raising it to the third power. So this is a multi-layered chain rule problem. Outer function is something to the third power, so its derivative is 3 times something squared. Middle layer function is sine of something, so its derivative is cosine of something. Inner function is 1 minus 2x, its derivative is negative 2. So when we multiply all of those together, it looks like D is our answer. All right, next page. I created all this extra space, but I'm just using a really tiny pen to squeeze it in. All right, another example where we're just kind of cranking out what the derivative is. Not a lot of deep thought here, we're just applying rules. So y is, x squared times e to the 1 over x. So by the product rule, my derivative here is derivative of the first times the second. That's easy enough. Plus the first times the derivative of the second, which would be e to the 1 over x times the derivative of 1 over x, which you can check is negative 1 over x squared. So this part really doesn't simplify. Over here, we'll notice the x squared and 1 over x squared cancel, and we just are left with a negative. So that e to the 1 over x factors out, and we're left with 2x minus 1, which is B. Okay, number 8. A point moves along the curve y equals x squared plus 1 so that the x coordinate is increasing at a constant rate of 3/2 units per second. So the rate at which x changes with respect to time is 3/2. So it's asking, what is the rate at which the distance from the origin is changing when the point has coordinates 1, 2? So this is an overly elaborate problem for number 8. Every single step should make sense to you, but I do want to make it clear that this is asking you to do way too much in 2 minutes. The Barron's book does overreach sometimes. So let's take a look at this. I'm going to draw a little picture just to organize what's going on. Here is my point, and my point's at x comma y, but it's a point on that curve, so I'm actually just going to call it x comma x squared plus 1. And I want to measure this distance between that point and the origin. So this is a related rates problem, actually. So what do I know? I know that this is 0, 0. Right? You can think of this as Pythagorean theorem. That's actually easier than the distance formula. So x squared plus 1 squared equals d squared. Just by the Pythagorean theorem. Now I'm going to take derivatives of everything with respect to time. Time is the underlying variable here, right? Because we want to know in the units per second. So there's a lot of chain rule stuff. X is not the variable. X is a function of time. So my derivative here would be 2 times x times dx dt. My derivative here would be 2 times x squared plus 1 times, by the chain rule, the derivative inside, which is 2 times x times dx dt times 0. And then here we have 2 times d times dd dt. It's a little awkward. I'm saying capital D for distance. And we have some specifics that the point is 1, 2. So my specific is that x equals 1. And if x equals 1, you can check that the distance is root 5. We also know that dx dt is 3/2. So when I plug in all those specifics, I have 2 times 1 times 3/2 plus 2 times 1 squared plus 1 is 2 times here 2 times 1 times 3/2 times 0 equals 2 times root 5 times dd dt. So continuing down here, I have 3 plus 4 times, what do I have in here? 3, that's 3 in there, equals 2 root 5 dd dt. So it looks like I have 15 equals 2 root 5 dd dt. So dd dt, oops, X. I don't know what's going on. dd dt, do it over here on the side, would be 15 over 2 times root 5. If you multiply top and bottom by root 5 to rationalize that, we have 15 root 5 over 10, which is 3 root 5 over 2. And is that a choice? That is B. So that's a lot to do in 2 minutes. All right, number 9. This is something you should recognize as the definition of the derivative, right? H approaching 0. If I wrote this as the square root of 25, it would be more obvious that we're following that pattern. What this is really saying is I have the function that's the square root function. And this is basically saying, what's the derivative of that when x equals 25? By the definition of the derivative, that's what the derivative is actually calculating. And that is a pattern you really ought to know. So by our shortcut, the derivative here is 1/2 times x to the negative 1/2. If I plug in 25, I would have 1/2 times 1/5, which is 1/10, which is B. You could also do this by L'Hopital's rule. It's basically the same amount of work. All right, number 10. Let me copy this and do it in a different place. All right, so number 10, it's a volume problem. So this is hard to see. That's a 4th root. So we have a region in the first quadrant bounded by that graph. And it's not clear how this works, but you might notice that in order to compute 1 minus x squared, x has to be smaller than 1. So the graph looks something like so. It's not a quarter circle, it's more exaggerated. But this region is basically the base, and you want to imagine of a solid coming up from that. This is the bottom, and imagine something coming up towards you. Each cross-section perpendicular to the x-axis is a square with one edge in that plane. So the idea is, think of that as the bottom of a square. That red segment is the bottom of the square, and then here are the other sides of the square, and imagine that square rising up out of the blue region towards you. So this is the side view. This is basically the top view. We have a basic principle that says we get volume by integrating the area of each slice. How do we find the area of a square? It's side squared. How long is this squared? Well, it's just the distance. How long is this side? It's just the distance between where this graph is and the bottom. So that side is the 4th root of 1 minus x squared. So area is the 4th root of 1 minus x squared squared, which works out to the square root of 1x squared. So my volume is the integral from 0 to 1 of the square root of 1 minus x squared. And this problem is beyond the pale for the real AP, because you don't know how to do this by the fundamental theorem of calculus. It would have to occur to you that this is the formula for a semicircle. So what this is actually asking you to compute is what is this area for a quarter of a circle. This gives us the top of the unit circle. So basically, what is that area? Well, it's 1/4 of the area of the circle that has a radius of 1. So our answer there is pi over 4, which is A. But I think it's completely unreasonable to assume that you would notice to do it like that, and all in 2 minutes. All right, number 11. This is a U substitution problem. I would encourage you to try to do it in your head. So the idea is we kind of notice that 9 minus x squared, on the one hand, we're doing something to it. On the other hand, we have something that looks like its derivative. So you can just kind of do this by guess and check. I have 9 minus x squared essentially to the negative 1/2 power. So let's suppose I started with 9 minus x squared to the 1/2 power. The derivative there would be 1/2 times 9 minus x squared to the negative 1/2 times, by the chain rule, the derivative inside, which is negative 2x. And that simplifies to negative x. Let's write it this way. That simplifies to negative x over the square root of 9 minus x squared. Right, the 2 and the 1/2 cancel, but there's a negative x, and then this is, negative 1/2 means a radical in the denominator. What do we want? We want the opposite of that. So how do we fix that? We can fix that by just negating everything. Right? I'll fix this. Oh, this is freezing for some reason. Let's just close it and reopen it. There we go. I can fix this by just adjusting, right? Multiply by negative 1, multiply by negative 1, that becomes a positive. So this would be our antiderivative, which is c, right? I'm leaving out the plus c. Obviously, you know to add that later on. So 11 is c. Now 12 is a trick. You don't do 12 by applying some slick rule or substitution. You do 12 by starting out by just rewriting this thing. Expand that and break it into 3 different fractions that you know. Y squared over y simplifies to 1/2 y. Negative 2y over y simplifies to negative 1. 1 over 2y you could think of as 1/2 times 1 over y. So what is our antiderivative? We can just do it one term at a time. My antiderivative would be 1/2 times, let me do a darker color. My antiderivative would be 1/2 times 1/2 y squared minus y plus 1/2, 1 over x or 1 over y is that special rule where it's natural log. So what do we got here? Which one of these works? It looks like it is A. In theory, you could just take the derivative of each of these. Same with number 11. All right, 13 is a bit tricky. Cotangent you probably haven't memorized, but let's think about this. If I want to do the integral of cotangent x, cotangent is cosine of x over sine x. And this you can do, oh, what happened? Somehow I lost that whole page. Oh no, I lost that whole page. That is strange. Okay, but where were we? I'll just take another picture of it. We were about to do problem number 13. So I'm going to take a picture of problems 13 and 14. This is pretty informal, so hopefully people will be okay with this. All right, so for number 13, I need to take an integral of cotangent. Let's not worry about the bounds right now. That's the integral of cosine of x over sine of x. This might not be obvious, but it is a substitution problem. If u is sine of x, then up top we have the derivative. So what we actually have here is the natural log of sine of x. Right? Maybe that's not obvious, but if I were to actually take the derivative of this using chain rule, if y is the natural log of sine of x, then what do I have? By the chain rule, well, the derivative of the natural log of something is 1 over that something. And then by the chain rule, the derivative of what's inside is the derivative of sine of x, which is cosine x. So we do get cosine over sine. So if we add those bounds by the fundamental theorem of calculus, we have the natural log of the absolute value of sine of x from pi over 6 to pi over 12. So we have the natural log of sine of pi over 12. These are positive numbers, so I'm leaving out the absolute value. Minus the natural log of sine of pi over 6. Sine of pi over 2 is 1, so this is the natural log of 1. Sine of pi over 6 is 1/2, so this is the natural log of 1/2. Natural log of 1 is 0, so we have negative natural log of 1/2. Now, what's super tricky here is that that's not listed. But you may remember there's a logarithmic rule that says, right, let's think of this as -1 times natural log of 2. I can take that exponent and I can take that coefficient and make it an exponent. So this is the same as the natural log of 1/2 raised to the -1 power, which is the natural log of 2. I think seeing that this is a U substitution problem in the first place is really right on the boundary of what's acceptable on the AP and probably too far. And then this trickery where you get an answer that doesn't seem like it's there. I don't think this would really come up. Okay, number 14. This one is more conceptual. And I do feel like the actual AP emphasizes concept a little more than these Barron's books. So here's f prime. So let's just make some quick observations. F prime is positive between 0 and 2. So f, I recommend just thinking about f before you look at the choices. We know f is increasing on the interval from 0 to 2. And then f prime is negative between 2 and 3. So f is decreasing on the interval from 2 to 3. So let's just look at those to see if we can rule something out. We want increasing from 0 to 2, decreasing from 2 to 3. So 1 is still in the running, 2 is out, and 3 is still in the running. Okay, now let's look at 1 and 3. What you might notice is they're the exactly same shape, just 1 is shifted up. So the graph here and the graph here would have the same derivative, because the steepnesses as I move across here and the steepnesses as I move across number 3 are exactly the same. So if one of these works, so does the other. So 1 and 3 are both correct for number 14. And I will just double check that. I am looking at all the answers as we go. All right, and I'm going to do these 15 at a time. So the last one is number 15. There's a verbal description here. So the first woman officially timed in a marathon was Violet Piercy of Great Britain in 1926. Her record of 3:40.22 stood until 1963, mostly because of a lack of women competitors. Right? Just FYI, this is just my letting you know, because I'm a marathon runner. This is the current women's record. It was set a couple years ago in Chicago. Way faster. So it stood for a long time, but then shortly after 1963, times began dropping rapidly. Then lately, they've been declining at a much slower rate. So let M of t be the curve that best represents winning marathon times. So starting in the year 1963, what are they saying happened? The winning times dropped rapidly, but lately they've been declining at a much slower rate. So everything has always been declining, right? Declining rapidly, then declining slowly. Our graph looks something like that. And this is our graph of M of t. So which would be positive? Is M of t positive? Yeah, because that measures the times. The times are definitely positive. How about M prime? Well, this is decreasing, so M prime is negative. How about M double prime? Well, this graph, because of how it's curling, is concave up. If the graph is concave up, that means M double prime is positive. So 1 and 3 are the positive ones. So that is C. All right, so I'll do these 15 at a time, and another video coming up soon will have 16,